The ocean acidification versus pH change versus calcification. So this is a very important process, and we have to understand this. The very purpose of studying ocean acidification is nothing but to understand how the calcification is affected. So that is the overall objective of understanding about ocean acidification. So the dissolution of CO2 in water leads to ocean acidification. That's what we have been seeing so far. This leads to declining or reduction in the pH, that is increase in the H plus ion concentration happens. When the more H plus ions are present, it converts carbonate anion to bicarbonate. So there is a reduction in the carbonate ion concentration. So this is the major change that is happening. Under more partial pressure of carbon dioxide, the solubility of calcium carbonate, that is the saturation state of biologically important form of calcium carbonate, is affected. So this is what is the major change that we are actually worried about. The ocean acidification leads to dissolution of calcium carbonate. So increasing the river runoff and the sea ice melt are further diluting the seawater, causing additional dissolution. So this is what we are actually going to understand. Now, solubility of calcium carbonate in water. Basically, the acidification increases the solubility of calcium carbonate mineral, that is calcium carbonate with water and CO2 gives calcium 2 plus ion bicarbonate anions. When we heat the calcium carbonate solution, we expect more calcium carbonate to dissolve. So this is what is simple understanding, like when any salt or any metal, any chemical is dissolved in water, so increase the temperature, obviously they will dissolve more. So that is what is the basic understanding we have. But we see some precipitation when we heat the calcium carbonate solution. So when the temperature increases, the calcium carbonate is actually getting converted to calcium oxide and carbon dioxide. When the temperature increases, calcium carbonate is getting converted to calcium oxide and carbon dioxide. So this is the main thing we have to keep in mind. Temperature increases, carbon dioxide is produced more. The calcium oxide is insoluble in water. So when the calcium carbonate solution is heated, we see sediments getting precipitated, and we assume that calcium carbonate is less soluble in water. But in fact, there is a chemical reaction that is taking place and not a simple dissolution. So we also saw the hydrolysis and dissolution earlier. So in reality, what is actually happening is a chemical reaction occurring and not a simple dissolution or a physical process. So that's the reason calcium carbonate gives calcium oxide and carbon dioxide. Let us look at the saturation state of calcium carbonate. The stability of a mineral such as calcium carbonate is defined by a term called the saturation state, or omega. So this is given by omega form is calcium 2 plus into carbonate 2 minus and the apparent solubility product, that is given here, divided by solubility product. When the calcium is abundant in seawater, the saturation state of calcium carbonate mineral is mainly controlled by the carbonate ion or the limiting ion in the seawater. When the carbonate ion is high, omega aragonite is high and mineral formation is favored. So when omega aragonite is more than 1. When the carbonate concentration, ion concentration is low, the omega is low and the mineral formation is not favored. That means omega aragonite is less than 1. When the omega aragonite is below the value of 1, the water is termed corrosive because dissolution of pure aragonite and unprotected aragonite shells will begin to occur. So dissolution of these two things actually occur. So that is why it is called as a corrosive. Corrosive in a sense, it will dissolve. So that is a simple term. Calcium carbonate, which is the driver of many changes, we are going to see what are they. Both carbonates and calcium 2 plus ion play vital role in ocean chemistry. That's what we have seen. So respiration, calcification, photosynthesis and reproduction are all sensitive to concentration of carbon dioxide. The shell has two components. One is the organic framework, that is basically polysaccharides and glycoproteins, which control the formation of calcium carbonate crystals. They control the rate, polymorphic form, thickness and the length of this calcium carbonate crystal formation, which is basically the shell formation. So secretion of ammonia, which originates from urea, is converted to ammonium ions, because we have seen earlier also under acidic conditions what happens is like ammonia is getting converted to ammonium ions. So this is the only nitrogenous form which is affected because of the change in the seawater pH. The presence of an ammonium ion raises the pH of the extrapallial liquid fluid, favoring the deposition of calcium carbonate. So this is the overall process that is happening. The shell formation, which is called as a biocalcification, results in the CO2 production, reduction in total dissolved inorganic carbon, and a decline in alkalinity. So the dissolution of calcium carbonate results in the inverse of this one. So that is what the forward process is. The biocalcification is the one we are actually looking for. That means formation of calcium carbonate should be there. But when the carbon dioxide increases, what happens is the calcium carbonate actually gets converted to Ca2 plus ion and bicarbonate ion. The reverse reaction actually takes place. We have seen two major species, one is the aragonite and the calcite. So the aragonite and calcites are basically polymorphs of calcium carbonate. These are diamorphs. Rather than poly multiple, there are only two, so these are called diamorphs. The aragonite has an orthorhombic structure and calcite has a trigonal structures. Calcite is easily dissolved and its component ions are released to precipitate elsewhere. So this is the chemical process that is happening. The aragonite is the denser than calcite and it is a high temperature modification of anhydrous calcium carbonate mineral. So here is the example of the calcite and here is another example of the aragonite which are given here. So you can see aragonite is a very strong material and it is bulky also. So this aragonite, which is denser than calcite, is the high temperature modification of anhydrous calcium carbonate mineral. It precipitates as an unstable phase in aqueous media. Magnesium 2 plus ions are also well known to promote aragonite over calcite nucleation and crystal growth in low temperature condition. This is magnification of calcite, that's what we had seen earlier. So the calcite has a non-metallic luster and commonly clearish to whitish to yellowish to grayish in color. So there is a different grades of calcites are known. And it is moderately soft and it is moderately lightweight and has a hexagonal crystals and a rhombohedral cleavage. Aragonite is more water soluble than calcite. So this is one thing we have to keep in mind. The many marine animals including corals, snails, clam, etc. they use calcite and aragonite to form their shells and hard parts. So if they use aragonite, and they may be more water soluble. So deep sea mollusk they produce, which is natural pearl, are thin and aragonistic, while many coastal ones are thick and calcitic. So that means within the same species, for example mollusk, some of them are having aragonistic and some of them are calcitic. So many mollusk shells are aragonite on the inside and calcite on the outside. So they can use both the forms of calcium carbonate. The nucleation and growth of the aragonite versus calcite in the marine surroundings are affected by the pH, fluid, magnesium to calcium ratio, partial pressure of carbon dioxide, the degree of supersaturation, and diverse strategies to inhibit calcite nucleation and growth. So these are all the various things that are being carried out by the animals and the shells which exist in the sea. So the aragonite saturation states are studied in the Canadian Arctic region. So the color change from 0.5 to 2.5, the red color to the blue color, you can see the difference. So Baffin Bay area has a particular type of aragonite structures, and Labrador Sea having a different thing, David Strait or Amundsen Gulf or Barrow Strait. So all these regions have a different amount of aragonite saturation states. So when we look at the seasonal and the long-term changes in surface seawater carbon dioxide and carbonate chemistry, what we can understand is the low salinity and high seasonal temperature variability happens. Why that happens is because during the winter mixing, upwelling and the fresh water or the fresh surface water in the summer or fall due to increased precipitation. All these things affect the salinity. In other words, the salinity reduces because more water is coming or more input water happens. Similarly, the seasonal variability in dissolved inorganic carbon, this happens due to the salinity change. And we have also earlier seen about the Revel factor, so the buffering capacity of the surface waters. So the higher Revel factor values reflect that reduced capacity to absorb CO2 from the atmosphere. So these are all the changes that will happen, and these are long-term changes which are happening. And of course, pH, when we talk about the surface partial pressure of carbon dioxide and the pH exhibit mirrored seasonal changes. So that means winter it will have one pattern and in the summer it will have a different type of process. So how the animals mitigate, or when humans want to do some changes, for example, we have to reduce the CO2 so that the ocean acidification can be reduced. So what we can do, mitigation and adaptation strategies to reduce the CO2. One is mainly if we can focus on CO2 emission, that is we have to move from renewable, transition to renewable energy from the normal coal and other type of sources which you use for energy production. We have to improve the energy efficiency and the carbon capture and storage. And marine protected areas, like we have to establish these kind of areas to conserve the marine ecosystem and biodiversity so that pollution and other thing does not reach these areas. And we have to increase the alkalinity of the ocean. So how do we do that? We add alkaline substances to seawater to increase its capacity to neutralize the acidity. So in many places people are actually doing this in a very large scale. We can also use sustainable fisheries management, like we implement policies to manage fish stock sustainability, because we don't over catch the fishes, so we have to control that, because if we do that, it will actually help maintain the ecosystem balance and the fishery productivity. And we also have to create the public awareness and education. So here this is very important that we have to raise the awareness about the causes and effects of ocean acidification.